Okay, this is video number 1 for lecture 9, and this is a copyrighted video, as you can see. All right, lecture 9 deals with something called a heap, but a heap has nothing to do with a heap that we've used before for dynamic memory, for the, allocating things on the heap with the new operator. This has nothing to do with that. This is a separate thing altogether. It's called the heap. And then also a priority queue, which is primarily what we're going to be talking about in this lecture, in this video. And then also we'll look at the standard template library, a priority queue. All right, just as a little review here, going back to lecture 8, we looked at a binary tree, and remember that a binary tree, at one node in a binary tree can point to at most 2 or 1 or none other nodes. So in this case, this right here, that's null, and that's null, and that's null, and that's null, and that, and so they don't point anywhere. But this one points to here, which in turn, this one points to here, which points to here, which points to here. So there's no relationship of the values in the tree. So we can't use a binary search on it. We can only do it linearly, searching sequentially, in some form. We looked at different ways of doing that, different traversals, tree traversals, in order, post order, pre-order traversals. But at any rate, we have to visit the nodes and look for it, whatever we're looking for. And so it's always O of n. And so there's really, other than the fact that it's, one node can point to 2, it's not really much of a tree. I mean, because it can become quite linear. So no big deal, but that's what it is, and that's what happens. And then we also looked at a binary search tree. Let me get it up here into focus. And at best, it's O of log n. Best meaning if it's balanced, okay. But if it's not balanced and it kind of starts going like this linearly, then it approaches O of n. Okay. So a binary search tree is good because on average, if you assume that maybe these are ID numbers. If the ID numbers are not biased, if they're not, already sorted when you put them into the tree, you should get some kind of a triangular shape, where it's more or less a triangle, more or less balanced, more or less balanced. And if that's the case, then it's going to be close to log n, O of log n. But because there are no other restrictions, it's possible that it also can become linear in nature too, and so it approaches the O of n. But remember, there's also a couple of things here. It's sorted in the sense that the parent is greater than its left child and less than its right child. So 100 is greater than 90, but 100 is less than 110. Likewise, 90 is greater than 80, but less than 95. So there's that relationship in a binary search tree that allows us to begin looking at the root. And if it's not found, then is it less? Yes, it is. And if it's less, then we can eliminate all of this. Of course, if it's greater, then we eliminate the left half. So we cut the tree in half each time. So that's why it's O of log n, assuming that it's reasonably balanced. But if it gets out of balance, no. All right, and then we briefly just took a look at an AVL tree. An AVL tree is a binary search tree, but it's always balanced. It can never be out of balance by more than one level. These are levels. Okay, so it can never be out of balance more than one level. If another one is added here, then something has to shift. It's hard to say there's about 7 different shifts that are possible, or I think 7 or 8 or 9, I don't know. But anyway, the point is something's got to shift. We'll just pretend like it goes over to here. Actually, it probably wouldn't do that. This would probably go up to here, and this one would probably shift down to here, and then this one would shift up to here. But at any rate, it always has to stay within, it can't approach any kind of a linear approach. It has to be never out of balance by more than one level. So it can be kind of like this, or whoops, kind of like that, or it can be kind of like that. Oops, it's not going to allow me to do that, I guess. I thought I could. I'll do it like that. Oops, okay, never mind. You guys know what I'm saying. But it can never be where it starts heading way down, you know, like that. Can't do that. And therefore, it's always O of log n. That's an AVL tree. Okay, so lecture 9 introduces us to another binary tree called a heap. And a heap has two properties that have to be met. One is the order property and one is the shape property. If it doesn't meet these two properties, if it doesn't have these two properties or whatever, then it's not a heap. It has to have these two properties. So the order property says that the parent must be greater than both of its children. Okay, and it is, right? 100 is greater than 90 or 80. Notice that the 90 is on the left here and 80 is on the right. With a binary search tree, remember, well, and even either way though, the one on the right had to be greater than 100. But so it has, you know, it's very different than a binary search tree. But there is still a relationship of the parent to its children. Okay. All right, so if you take the 90, you can see that 90 is greater than 60, and 90 is also greater than 70. And 60 is greater than 40, and 60 is greater than 6. Let's just put one more. We'll put a couple more here. We'll put one right here, and we'll put right here, and we'll put one right, kind of run out of room here. Put one right there. Okay, we'll do it like that. So let's say, so this one is 15, 12, 47, whatever, 3. And the reason why I wanted to do that was to make the point here that there's no real relationship between the nodes in the tree other than the relationship of the child to the parent. What I mean by that, here's a 3, which is very small, and it's on the same row, so to speak, as a 40. Okay, and also, you know, here's a 47 right next to the 3, and here's a 6 right next to the 40. So there's no relationship amongst the sisters and brothers. It's only, like in this case here, a 3 and a 47, those are both less than the parent. 12 and a 15, both less than 70. So that's the only relationship with the order property, is that the parent is greater than the children, but it doesn't matter which one of the children has the higher value. It could be the one on the left, or it could be the one on the right, like in this case 75 versus 78. Okay, so it can be, that's unimportant, left or right, but it does have to have that relationship of parent is greater than both children. If you recall, I believe that back in lecture 8, we had these terms about a binary tree. A tree could be complete or full. Those were terms, I believe they were in lecture 8, pretty sure. Remember that a full binary tree is a tree that is, I guess you might say, is full at a given level. So that would be a full, it's a perfect triangle. Okay, it has to be completely full. Every node except the leaves. These, remember, these were leaves, and the leaves have, none of the leaves have any children. They all have null pointers, you know, for their left and right pointers. That's full. Complete, though, if you recall, complete looks like this. It could be something like that. So it's only one level out, like that. Okay, it cannot be 2 levels out. So this is complete. So this one here would be, this one here is actually complete. It's complete and it's full, huh? This one is complete but not full. To be full, it would have to have the rest of them here, you know. Okay, but it doesn't. So it's complete but not full. That's just by definition. You know what complete and full means. Okay, so in summary then, a heap is a binary tree with these two properties, the order property and the shape property. If it doesn't satisfy those two properties, it's not a heap. So in this case here, this is a complete tree. So remember, a full tree, you know, would be a complete tree, of course. A full tree is a complete tree, but a complete tree is not necessarily full. In this case, it's not. This is not full, but it is complete. Okay, so it has to satisfy the shape property, and it has to satisfy the order property. The parent is greater than the children. By the way, in terms of the order property, then one thing is obvious then, I think. Okay. At any given moment, the root, if you want to call this the root, that's often called the root. At any point in time in a heap, the root would be the highest value, wouldn't it? Because it's greater than its two children, and each of those become parents of two, and it's greater than its two children. So at any given point, the highest value, sometimes referred to as the max value, but doesn't have to be called that. You know, the highest value is at the root. Okay. So if we want to insert something into the heap, we have to do it this way. We have to insert it at the bottom level, at the next available place to the left. In other words, we can put it right here. It has to be, well, it doesn't matter what it is. Let's say it's going to be an 80, just for example, 80. We put it there, and if we do it there, see, it satisfies the shape property. Oops, I'm not afraid it's going to do that. It satisfies the shape property, and that's good. And if we didn't do that, and we put it here, we'll say, like that, then we don't have a shape property. And we don't have the shape property. We don't have a complete tree. It's out of whack. Remember, it has to be like that. Now, in this case here, on the right here, if we were going to insert another one, it would have to go right here, because that way it's still a complete tree. And then if we do another one, it would have to go here. So it's still a complete tree. And then it would have to go here, and then here, and here, like that. So it always remains, you know, and then here, and then lastly here. And now it's still complete, and now it's full too, but that's neither here nor there. It's complete. So we can't do this. That won't work. We have to always insert at the bottom level and at the leftmost, I guess you could call that leftmost. So it'd have to go right here. And so it would be like that. So we have to always insert it so that we maintain the shape property. Okay, oops. So that's the idea. So that's the first thing. When we insert, we have to insert at the bottom level. This is a level, and we go from left to right. And when it gets completely full, then we go to the new level and do it again. But always at the, you know, like if there's two here, then the next one goes here. Always has to be in the bottom level, and then here goes left to right. Okay, so here's a heap. Did I do that correctly? This wouldn't be correct, would it? There we go. Remember, the parent has to be greater than its children. Okay, so if we were going to insert one in here, it would be right here. It'd be the next available one going left or right on that row, on that level. So let's say that we insert an 80. Okay, so again, the shape property is intact, but the order property is not, right? Because remember, the order property says that the parent has to be greater than both of its children. In this case, then, 70 is not greater than 80. So we have to do a swap. And we do. That's what happens. So then they swap, and the 70 goes here, and the 80 goes here. So this is part of the insert function, is to first place it to keep the order property intact. Excuse me, the shape property intact, and then do a swap so that the order property is intact. So now the parent is greater than the children. In this case, it only has one child. Okay, and then it compares with its parent. In this case, it's not greater. 80 is not greater than 100, so there's no swap, and it stops right there. So then if we insert another one, it would go right here, right? And let's say it's 110. So now the shape property is intact. It's complete and full in this case, but it's complete. And now it does a swap. It says, is the child greater than the parent? It is? Okay, swap. So then 110 here, 80 here. And then you can do this either in a recursive function or you can do it in a loop. Oops, this is 110, not 100. And so then, is 110 greater than 100? Yes, it is. Then swap. So 100 goes here, and 110 goes here. This idea of it swapping its way up is sometimes referred to as bubble up. I'll do it like that, like a function, a bubble up function, like the bubbles are bubbling up. Okay, I think in our particular lecture notes and so forth, it's called re-heap up. But it doesn't matter. It's just different textbooks have different names for it. But the idea is that you put it here, and then you swap it to here, and then you swap it to here. Or in this case here, it started here and it swapped to here, but 50 was not greater than 100 at that time, and so the reheap up stopped right away. So when you put one in here, then you reheap it, and then maybe it stops right there. You put another one right here, and maybe it's less than the parent, so you don't do anything, and so forth. And then you put another one here, and you reheap up, reheap up. Maybe it goes all the way up and swaps and ends up being here. So that's called reheap up or bubble up. Oftentimes those terms are used. And it's usually done recursively with a recursive function. The reheap up function, it handles, it's the code to do this reheaping up. But whenever part of what it's doing is checking, is the child greater than the parent? It's like an if else. If it is, then from inside the reheap up function, it calls a swap function, and it swaps the two. It swaps them. Okay, so a swap function it's a separate function from reheap up, but it's in a sense it's part of the reheap up function. Okay. Okay, so now we've talked about inserting into a heap, and again it would go right here. And if it's a 6 compared to the parent, it's greater. Okay, then swap. 4 goes here, 6 goes here. Greater than parent? No, it's not. 6 is not greater than 60, so it's done. The reheap up is done. Now to delete that's to insert, of course. Insert function then needs to use a reheap up function. Reheap up function. And then the delete function is going to use a function called reheap down. So when we delete, then we remove, or I shouldn't say we, but the item is removed from the root. So the idea is that we're going to with a heap, the idea is that we remove or delete the max item or the largest item. So we take away the root. All right, so if we take away the root, that was 100. Okay, now it leaves a void right here. So what we do is, let's see, I'm just going to say we have a 5 right here, just to put some up, and we have a 30 right here. Okay. Just doing it that way. So we remove the 100. And now what we do is we take the bottom level rightmost, this one right here, not the left, but the rightmost. I mean, if we had one here and we had one here and we had one here, we would take this one. It's always the one on the bottom level and the one to the far right, this one right here. Okay. See if I can just back this up a bit. So we'll say it's the 30. There we go. Whoops. Didn't mean to do that. So we'll do it like this. Okay, so we take away the 100, and so then we take the bottom rightmost one, which is this one right here, we'll say, and we move it up to the root. And by the way, when we remove the root, then we've lost our shape property. Now we have this kind of an effect. So we're no longer complete. But if we take this one right here and we move it up to here, then we now have, we're back to at least our shape is correct. Let me do this, I'll leave that like that. So this part is correct. And get rid of this guy. Okay, so now we're back to this approach. So we're back to at least our shape property is intact, you know, where we have something like that. Oops, like that, or I got to do it in pieces like that. So it's one of the two. So and now we're back to that. We have that approach. Okay. All right, but now we have this problem. Our order property is out of whack, because remember the order property says that the parent has to be greater than both of its children, and so that's not going to work. This one's gone too. Okay, so we use this reheap down function. So the parent then compares its right child. I guess I should do that as a lowercase r because it's actually a variable. Oh, stuck on it. Oh, there we go. And it compares, this is the right child, and this is the left child of this parent. Left child. Okay, and so the root, if it's greater than both of its children, then there's no swap. It's done. Like if this was 500, then of course there'd be no swap. It would be the largest one. But in this case, it's not. It's actually less than, you know, both of its children. We'll say this is 19 because I got some stuff there. So the root is actually less than both children, but we want the root to hold the highest value. So the root is going to swap with the max child. The max child, that's going to be a variable, as you'll see in the code. The max child then can be the left one or the right one, but because there's a left child and a right child, but the max child is going to be the highest of the two. Always will be the highest of the two. It's the largest value. And so it's 60. That's the max child. So the root then swaps with the max child. So the 60 goes here, and the 5 goes there. And then this is a recursive function called reheap down. So now the 5 is here. Of course, the shape property is fine. It's fine. Okay. So now the 5 compares with 6 and with 50. It sees that the max child is here. So it swaps. So this is 50. And this is 5. And now it's at there are no children beyond that. You know, it's just the null. So it stops. And so when it's done, what happened? It took the rightmost child, which was in the bottom row, which was the 5, moved it up to here after this was taken off, moved it up to here, and then it reheaped down to here. So when the dust settled, it was no longer here. It's now here. So it went from here up to here and then down to here. But in the end, the shape property is intact. It's a complete tree. And the order property is back intact, with the parent being greater than both of its children. So that's the delete. So in a heap then, the one that's removed is always the largest one. So no matter what this tree looks like, no matter what is in here, it's always going to sort of filter up so that the large one will always be there. And when it's removed, it always removes the largest. That's the data structure. That's what a heap does. It's a funny kind of sort, because they're actually not sorted in here. Only the largest one is at the top. Beyond that, here's a 5 and here's a 6 and an 8 and 4. I mean, they can be in any order. It doesn't matter at all. But it is like an AVL tree in the sense that it has to be a balanced binary tree. It can never be out of whack. Where it's how should I do that? Just where it's like that. It can only be one level. It has to be a complete tree. A complete tree is one level out. Okay. And that's what a heap is then. And so the advantage to a heap then, or I shouldn't say the advantage, but what the purpose of a heap then is to always remove the one that has the highest value, even though they can be put in down, when they're inserted in any order. You could insert 110, you could insert a 600, you could insert a 4, well, I got a 41. So it doesn't matter what order they're here, but they'll bubble up or reheap up to wherever they should go. And then when one's deleted up here, then the bottom rightmost one, which is this one right here, it will go up to here, and then it will reheap down to where it should go. And the new highest one will be up there. That's what a heap does. All right, so taking a look at our lecture notes here, we can see starting out the top, it says a heap, a binary tree that satisfies these special shape and order properties. Note this type of heap has nothing to do with a dynamic memory called the heap. Shape property, its shape must be a complete binary tree. Order property, for each node in the heap, the value stored in that node is greater than or equal to the value in each of its children. We won't worry about equal to. You can actually create a heap where you can have duplicate values, like you could have another 50 right here. But that does require, it's not a big deal, but it just requires more code. You have to consider the idea that there's duplicates. We won't do that. We'll assume then that each value in the heap will be a unique value. That's often called a primary key. If you deal with databases has tables. Here's a database table. I won't get sidetracked for long, I promise. And this is how data is stored all over the world. By the way, some of you might have an interest in it. Being a database administrator, which is a computer science degree, is a very lucrative and sought after occupation. So you might consider that. There's different universities that offer that as one of the tracks for a computer science degree. But basically, data is kept in tables. This is a table, and the tables can be related together. I'll do a little mini drawing. Here's a table with a bunch of fields, and it can actually be joined. The term is usually called join or joined to another table, like linked together, which in turn could be linked to another table. And each one of these is a table in the data. The whole thing is one database, but you can have lots of tables. Anyway, within a particular table, you can have records. Each row, this is one record all the way. We'll just say to there. That's a record. And then here's a record, and here's a record. And here's a record, and here's a record, here's a record, like that. Okay? And so I cannot explain to you how important databases are. The entire World Wide Web works on databases. Google is nothing more than just a giant database company. Web pages kept in database tables. Somehow you have to be able to access data quickly. And so if you store it in tables, and then you have one particular field, these are all fields. Each column is a field. And if you have one particular field that where the values are unique, then it's usually called a primary key. A primary key then is just, it's a field. But it's different than the other fields because it all the values are unique, no duplicates. So it has to have unique values. And so usually it's the ID field, because everybody has a unique identification number. Because you can have two people named Tom Lee or Kim Smith or Joe Jones or whatever. You could have many people. You could have 20 people named Bob Smith at a school, or Robert Smith or something. But if each student has a unique identification number, and they do, your ID number for a school is going to be unique. It's not going to be the same as anybody else's. And that's pretty much how the world works with databases and database tables. There's usually one field that is the primary key field, and no duplicates are allowed. That makes it easy to search and find that particular person, because otherwise, if you made the primary key be first name or last name or something, well, that's really sketchy, because you could go into the office and say that you're Tom Lee and you'd like to get your whatever, pay some money or get your transcripts or something, and there could be 10 Tom Lees. So it has to be a primary key almost always in a database. It's not required, but it's highly unusual to not have it. Okay, so anyway, that's the point there, is that it says that somewhere, I forget where we left off, in fact, but that could be duplicates, but really, for the most part, the primary key field, there should be no duplicates. And that's how you would find any particular record in this heap. You can delete it off there, and these could be not just numbers, but these could be struct or class objects, and so they can have a lot of data in it. So you have one field, the primary key field, is the identification numbers. And if you think about it, everything from driver's licenses are unique to social security numbers are unique. Even when you sign up for classes, CRN is or ISBN for books, those are all primary keys. Those are all primary keys. All right. Well, anyway, this is not a heap. And you can see why. The order property is fine, or excuse me, the shape property is fine, but not the order property, because the parent has to be greater than its children, and C is not greater than T, assuming you're going by the ASCII table. I think a T is an 84, and this is a 67 or something. So no, not a heap. This one here, though, yep, every parent is greater than his children. Delete the largest element. That's the algorithm. Delete the largest value in the heap, delete the root. This leaves a hole at the root, and we know that because it'd be kind of like that, wouldn't it? If you take this one off, then you're left with that. So take the bottom rightmost, let's say we have a couple like here. We take that one right there. We take it and move it up to here. So now the shape property is fine. So it's a complete tree. But the order property is out of whack, because this one is likely not going to be the highest one. Could be, but probably not. So now all elements now all elements satisfy the order property except for the new root. Fix the order by moving this element down until it ends up in a position where, in other words, swap it with the max child. Swap it again with the max child. Swap it again with the max child. Just sort of move it down. And so remember, that was the reheap down. So the delete function deletes the max item and then moves that up to there and then reheap down to reset the order property. Oh, here it is right here. Reheap down. Restores order. The element is moved down by swapping the root with the largest child, the max child. The result is that the root becomes the max child. This max child is then compared to its its children and swapped with the largest child, and so on and so on and so on. For inserting, without even reading this, remember if we had this tree right here, the insert would be right here, wouldn't it? Because it's in that whatever level it is, and it's the rightmost one. But again, remember that if you had something like this, you couldn't put it here. It would have to go right here. You can't have a hole. That wrecks the shape property. Okay. All right. And then we sort of change things here. We take a look at this heap as a binary tree, and we kind of look at it in levels. Or we can look at it in levels, it's sort of conceptually. Level 0, level 1, here it is. Level 2, like that. Level 0, 1, and 2, and so forth. So we can look at the binary tree like that, and then we can basically put them into an array. So where we're going to this, the bottom line to this whole thing is we're going to use the principles and the concepts of a heap, where the order and shape properties, but in terms of actually implementing this with programming code with C++, we're going to implement it as an array. So that's kind of an unusual thing. We haven't really done something like that before, where we talked about something conceptually with it like a list or a linked list or whatever, and then did it with an array. But in this case, that's the whole point of this lecture, is to first introduce what a heap is and say, okay, now that you know what a heap is, we're not going to use it. We're going to, well, in a sense we are doing it. It is a heap, but we're going to implement it as an array. So the array will hold values that satisfy the heap properties of order and shape. And that brings us to the data structure called a priority queue. It's basically an array-based data structure that implements the principles of a heap, where the highest priority or the highest value is accessed or removed from the priority queue or the array. It's removed first. That's what a priority queue is. The highest priority. In other words, it's a queue, but remember, you guys, I usually do it sideways. Here's a queue. And remember how that works? The first one in, how shall I say this, is first one in is the first one out, right? FIFO. And we in-queue from the back, and we remove from the front, DQ from the front. And we studied that with a circular queue. In FIFO, first in, first out. And that's fine for a queue, but in this case, this is a queue, but instead of being first in, first out, I'll draw it this way then. It's not the first one in that's going to be the first one out. It could be this one down here that gets put in quite a bit later, but it's going to end up, it may end up being, when it gets inserted, it's going to swap, and it might end up being the max. It might end up being the root, the highest one. So it could be inserted here and then reheap up, and it might be the first one that comes out because it might be the highest value. So the highest value ends up reheaping up to be the top. And if it's at the top, the highest value is the highest priority. So it's not a first in, first out. It's highest one in is the first one out. I don't know how to say that in terms of an acronym, but that's what it is. The highest value is the first one that's removed. And so that's what a priority queue is, because it's sort of saying like the values have a priority, and the highest value has the highest priority. And so this has some real world applications for a print queue, for example, where you could the different people could have a different access code that could be used in the priority queue. Because you guys know in a queue, you've done that, what's called a print queue. I'll just do a letter Q. A print queue, then, when you're working on a network or on a school or in a school library or whatever, and you click File and Print, your request from your computer to print goes into a queue. And when if it's a typical queue first one in, first one out. And so therefore, if you are the 5th person to click print, then the 4 in front of you would print first and then you. But a priority queue would prioritize who prints. So if you're working for a company and you click print, you might have been ahead of the boss, but the boss might have a top priority ID number, so that when the boss puts it in here, it's going to reheap up and it's going to be at the top. We all have a boss, right? I don't know. I guess we do. Anyway, so that's a priority queue. That priority is, even though it was after several other people requested to print, it goes to the top. And that's what a priority queue is. It sort of weight, meaning like applies a weight, a value to each entry into the queue, and the highest value moves to the top of the queue. Okay, so just an example here. It says highest priority means different things, depends on the application. A phone answering service answers call in the order they are received. Highest priority call is the one that's waiting the longest. So even in that case, even though it really is a first in, first out, that would just basically be first in. The application, the program could go ahead and apply a timestamp or something, and so the oldest, the first one in is the first one out, and that's still a priority queue. Operating systems use priority queues to determine which process to run next, and that happens a lot. There can be several different processes to run. When you're using your computer, your operating system has to balance all these different processes. You might be using Microsoft Word, and you've got a Norton antivirus program running in the background, and I don't know what else you've got. Something else going on. Different kinds of programs. And so lots of different kinds of programs, but the operating system will put these into a queue, and a priority queue, and if one has higher priority, it will bubble up or reheap up and become the next one to execute. And the operating system is basically letting Microsoft Word execute for a while, and then it lets Norton antivirus for a while, then it goes to some other program for a while, then back to Word, and and occasionally this. Some of these might have a very low priority. Some of these processes, they could run in the middle of the night, and they may sort of stay low in the queue for hours, and eventually they'll reap up in the middle of the night and execute or something. So the ones that are higher priority will execute right away. If you downloaded a file, if you were working on something on your computer and you put in a request to download a file off the web, that file is being downloaded into your computer. That takes time. In the meantime, you could do something else, or maybe Norton antivirus is running, doing stuff in the computer. And then when the file is completely downloaded and it's in the computer, it can cause an interrupt. I think it's 2 R's, interrupt. And interrupt what's going on. And that tells the operating system, hey, the file's downloaded. Let it have priority. And it will move it to the top of the queue. And when Norton antivirus finishes its little segment that it's running, then it will be removed, and now the file interrupt has moved to the top, and it will then execute that next. So an interrupt, there's all different kinds of interrupts. Interrupts interrupt the operating system. A file is completely downloaded. It's time for it to do something, or whatever. And so those interrupts can move the process to the top of the queue. Okay. All right, so that's kind of the idea there for a priority queue. It just simply prioritizes things and executes the highest priority first, which back in the heap binary tree heap, the top priority was this one right here, and it's removed like that. And then this is brought up, and then it reheaps down, swaps. All right, so then here's the priority queue abstract data type, the class, in other words. priority queue class includes many of the same member functions as other queues, and we've done that with queues. Is empty and is full, checks to see if the queue is empty or full. We can make it empty. In queue, I don't know why I get the extra U's on there. I think probably more appropriate should just be like that. But anyway, doesn't matter. In queue means to put it on the queue, push it on the queue if you want to use a stack term. So the first 3 or 4 pages of the lecture notes just explains what we've just gone through, what a heap is and what a priority queue is, and how a priority queue basically implements a heap, but does so using an array. So here's the code. By the way, for a quiz or an exam, there won't be any questions about the code because the code would be difficult to memorize. And so for the sake of studying for a final exam or whatever, or a quiz, just know the concepts of what a heap is and what a priority queue is, and how things are, how something is inserted into a heap and how something is removed from a heap, and so forth and so on. So we're going to look over the code. There's one more thing I wanted to mention going back to the array, which we haven't discussed, and then we'll take a look at the code. Okay, so here is a heap, and I didn't really stress this point, and I would like for you to know how this works, so to speak. Remember that the parent is greater than the left child and the right child, but either the left or the right can be the max child. In this case, the left child is the max child. Well, for that case, so is this here. But anyway, it could be the left or the right child. But notice here then, if we look at these in terms of levels, we can look at this as the 0 element, and then this is 1, and we can look at it using this formula that the left child is the root times 2 plus 1. So 2 times 0 plus 1 is 1. And then the right child is root times 0, which is 0, plus 2. So if we take this one, this is a 1. So 2 times 1 is 2 plus 1 is 3. And 2 times 1 plus 2 is 4. See, so the relationship holds the same here. Whatever the root is, the left child is going to be 2 times that element plus 1. And the right child will be 2 times that element plus 2. So they can be put into the array using this relationship. So 70 goes right here. So 2 times 0 plus 1 is the left child. This one right here. And then 2 times 0 plus 2 is 2. That's the right child. But now if we take the 60, 2 times 1 is 2, plus 1 more is 3. So this one here ends up being the left child of this one right here. And 2 times 1 plus 2, this one right here, is the right child of this. And so on and so on and so forth. So what do we have here? We have this one here, that's right here, index 2. 2 times 2 plus 1 is 5. So here's the left child of right here. And now there isn't one here, but if there was one here, we'll make it a 9 or something, doesn't matter. Let's pretend like it's a 9. That would be 2 times 2 is 4 plus 2 is 6. It would go right here. And that'd be the right child. So that's the relationship. It's using a heap conceptually, but they're placed into the array using this formula, or it's accessing the elements in the array using this formula. The left child is 2 times the root plus 2. The right child is 2 times plus 1, or plus 1 plus, you know what I'm saying. So for example, say this one right here. So that if that's the parent, that one's, which one is that one? That's this right here, isn't it? So then if we wanted to know what these are, it'd be 2 times 4 plus 1 is 9. So 7, 8, 9 right here. That would be the left child of here. And 2 times the root plus 2 would be the right child. So as you can see, as this array gets bigger, as it grows longer, then the root and its two children, there becomes a bigger space in between. Right? See here, right here, there's no space at all. They're right next to each other, the first three. But then they begin to separate with those spaces in between. And so you can see on an array that has a million elements, the left child is 2 times the root plus 1. So if it's 50, if it's index 50, then the left child is going to be 101, isn't it? 2 times 50 is 100 plus 1 is 101. And the right child, this would be the left child, and this is the parent. And the right child would be 102. So you can see there starts to be a lot of items in between. Not that it really matters. It's just because the tree is spreading out, so to speak. So when they're placed into the array, they are spread out as it gets further down the array. But it doesn't really matter. It's just a simple mathematical formula. But that's how it's able to keep this relationship and so forth. In other words, how to implement a tree into an array by maintaining this formula here. Okay, now we get down to the actual code, and the code it actually implements 2 classes. That's what I was saying, is there's not going to be any questions on code. It'll just be on the concepts of what a heap is and what a priority queue is. There could be some diagrams. You'll have some homework to do that'll have diagrams on inserting or deleting, into a priority queue or a heap for that matter. So anyway, we'll take a look at it here. Let's flip over to here for a second. Here, the code basically is this. I just itemized out the different. There's actually 2 classes. There's 2 classes: heap type and priority queue. So the heap type class, everything is public. By the way, I'm sure there are many ways you could probably implement this priority queue, but this is just the way that I don't even remember where I got this code. I got it out of a textbook at some point. But basically, the heap type is entirely public. So at first glance, you'd think like, well, that's not normal. Normally, you don't have anything. You usually have something private. But a heap type object is right here. And a heap type object is actually a private member of the priority queue class. So the fact that all of these are public doesn't really matter much, because a heap type object is private. And a heap type object that's private means that only these functions here, these in the priority queue class, these are the only functions that can act on this private data member. And this is an object of heap type. And what's inside of heap type? All the stuff that maintains, what a heap is. Reheap down, reheap up, and swap. That's really basically it. This is a pointer that's very important. It's called elements, but you could call it pointer. You don't have to call it elements. But in this particular, code, it's example, it's called elements. But it's just a pointer. And of course, the priority queue, and the heap itself, it's going to be implemented as an array. And so it's all going to be based on this right here. This pointer is going to point to the array. Okay? But remember then that these are all public functions, so they can be accessed down here. So for example, enqueue, that's when you put something into the priority queue or into the heap, then it's going to put something in and then reheap up. So inside of the enqueue function is a reheap up function. Dequeue means take something out, and so it'll be reheap down. So which are right up here. Here they are. So again, this entire heap type class is actually implemented right here as a private object of the priority queue class. Okay, so the pointer is in heap type, and it's going to use the new operator to dynamically allocate an array. we'll see that code. So it's a fairly complex thing, but it works fine. You know, so basically the priority queue class right here has real typical functions: make empty, is full, enqueue, and dequeue. These are functions that we've used before, and this is the constructor and destructor. So these are very typical queue type of functions. It's the heap type class that actually maintains the heap properties and also you know, makes it a priority queue implemented by an array. All right, so we'll walk through this. You don't need to know this code. I'm not going to ask you any questions about it as far as the pointers or anything about it. So just kind of absorb it. But what I would do if I were you is I would keep this code. You might need a priority queue in the future, and you know, at your university studies, and you'd have one already ready to go. Okay, so here's the heap type class, and note, I don't know why I did that. I don't know if I just copied out of a book that way or what, but I've got public listed twice, which isn't necessary. Just because these are functions, they could all of these things could be listed under one public category, so to speak. They're all public, so there was no need to put public twice. Here's the pointer. It's called elements, but that's no big deal. And notice then we have in the heap type class, we have the functions that really maintain the behavior of a heap, which is, you know, critical for a priority queue. Reheap up, reheap down, swap. We're not going to go into the details of the reheap. These are recursive in nature. See, here's the function call, reheap, sending the root and parent, and it's inside the reheap function. So it's a recursive function, just because remember what reheap does for reheap up, if you recall. Whoops, stuck on it. Remember how this works. Remember when we enqueue, we put it at the bottom rightmost to maintain the, you know, the shape property. So it goes right here, and then remember what we do, we compare this one to its parent, and if it's greater than the parent, we swap. And this swapping and now it's here, and then it compares it to its parent, and if it's greater than this parent, they're swapped again. So it's reheaping up, it's moving up, and it finally stops at some point because it is not great. The parent is greater than it. I'll put it that way. So that's what this is doing. This is reheap up, and if this is true, that it's greater than the parent, or the parent is less than the one, then swap them. Okay, and then after swapping, reheap up again. Goes back up to here. So forth and so on. You can go through this and figure out why it's doing that, but that's basically in a nutshell what it's doing. Reheap up then does call a swap function as it moves up, and it's done recursively. And then here's the swap function right here. Oops, right, hang on one second, just wanted to move that down. There we go. So here's the swap function, just sending two items to it, and they get swapped. This is a typical swap algorithm. You can look it over later if you're not sure how that works. Whoops, doggone it. Here's reheap down then. Remember how that works when we have a heap and we take this one off. Then we take, we'll just say it's this one right here. Remember, we take the bottom rightmost one and we move it up to here, because see, it's not the shape is not correct, so we put it right here. We take this one and put it right here, but now that it's here, that's now the shape is correct, but the order is not, because this one, it's unlikely that that's going to be the highest one. So then it has to reheap down by swapping with the max child, which is one of these two. Whichever one of these two is bigger, it swaps. So the reheap, see, so now it's moving down. It gets put up here, now it works its way back down to some point. Okay, That's the idea. So the reheap down also has a swap function in it. In fact, it's the same swap function. It's called from when here's reheap down, and so there's a swap in here. Where is it at? Right here. It swaps. See here, it's checking to see if which child is it. Is the right child the max child? Max child is the right child, or max child is the left child? That's all that's determining, because it needs to know which child, which one's the max child, because it swaps with the max child. See, so after it finds out, then it swaps it with the max child. Anyway, we're not going to go through the code. We're just kind of we're going through it, but we're not. It's not something you have to memorize. All right. I don't know where we left off. Here's the priority queue. I guess we haven't done that yet. And the idea I talked on the whiteboard there, I mentioned to you then that here's the actual heap type object. That's an object of heap type, and that's a private data member of priority queue. That's how it pulls together then. This right here is the object that's inside the priority queue. And this object then can be, because it's private, it can be accessed only by these public functions here. And these are very typical queue functions. We studied queues, and so that's what this is. This is very typical, is empty, make empty, is full, stuff like that. And all of those functions then can act on this object. Look at the constructor. Let's go to the constructor here. Yeah, here's the constructor. Max is just the size of the array that's passed from main. Let's take a look at that real quickly, then we'll come back. Here we go. So here's the priority queue object. It's just called queue. Okay, you can call it anything you want. Okay, and then here's what's being sent. It's calling an overloaded constructor, isn't it? And it's passing, well, okay, it's a 5, pretty small. So it's just saying, Q5. That's what it's sending to the constructor. So the max items is just the size of the queue. 5 is really, really small, of course, just making a point there. So going back to this then, right here in the priority queue constructor, this is what's passed from main. That's a 5. That's put into max items just so it keeps track of the maximum size or items in the array. And then here's remember, this is a pointer. Elements is a pointer. This is the object. This is the heap type object right here. That's the object. And remember, what a heap type object has is a pointer. Right, where's it at here? Here we go. Right here. Here's the pointer. And that's, so every heap type object has a pointer called elements in this particular case. All right, so going back to here, here's the object, and it's using the dot operator. Items dot elements is assigned, and again, this is a pointer. So really what it means is we've got this pointer called elements, and it holds the address. Let's pretend like it's 5,000. Holds the address of a new array on the heap. It's using the new operator. So this first byte right here is 5,000. So elements, the pointer, holds the address. It points to this new array, whatever it is. In this case, it's size 5, very small, just size 5. Okay, that's the idea. Okay, so that's how this data structure maintains the class integrity, so to speak. In other words, because the heap type itself, as mentioned before, is everything is public. And generally, you don't do that sort of thing. This is all public, even the data here, the variables. But because the whole heap type object is private inside the priority queue class, right here, that means that all of those public things in the heap type class, those are all private in a sense, because they can only be accessed by these functions here. So these functions here can use the pointer to create the new array, but also it can be used, well, to delete, of course, in the destructor, but also down here. Items is the object. It can call reheap down in the DQ, and in the InQ, items.reheap up. And oh, this is interesting here. Items.elements. This is the object, and this is the pointer. And the pointer is being dereferenced, I guess you might say, to length -1, because remember in a queue, just sort of by definition, it's always enqueued at the back. So length -1 would be the back element right here. If it's 5, it'd be index 4. Length is 5, -1 is 4. So remember, InQ from the rear, DQ from the front, right? Anyway, so it all makes sense. It's all it's still sticking to what a queue is, InQ from the back and DQ from the front, and yet it's using these functions that are in the heap type class, and it's using the object of the heap type called items to do so. So that's it. It basically creates a queue, but it behaves in a specific way, so we call it a priority queue, and it does so because the highest value is removed first, and then the other ones are shuffled, so to speak, reheaped up and down to maintain the integrity. And that's pretty much it. I'm going to go back up here to the top for a moment. Not there. Hang on. Right here, I would say. Let's see here. Yeah. So in this particular case, here we have a view of a heap, so to speak, and here we have a priority queue. And so remember how this works. If we remove the 70, that's the root, or here it's called tree, but you can call it tree or root. And that would be the same thing as removing this one, right? And then remember how it works? The bottom level rightmost is moved up to there. That's just what it does. So that would be this one right here. So when this one is removed, it's always going to be the last one in the array. So if this array was much larger, when this one is removed, let's just say there's stuff in all of these here, and right here is that. So when this one is removed, it's going to take this one. It always would take the last one, because it would be the last one right wherever that is, right here, is going to be the one right here. No matter, even if you go a bigger tree, it doesn't matter. Wherever the last one, the rightmost right here, the rightmost one is going to be that one right there. Okay, so whenever the root, or in this case it's called tree, whenever that one is deleted, which is right here, when it's deleted, the bottom rightmost is moved up to there. So when this one's deleted, the bottom rightmost is moved up to there. So that's nice. So this array could be 1,000,000 or 10 million, doesn't even matter. It's simply going to take the bottom element. This is going to be removed, and the bottom element is simply assigned to that location, index 0. So it's very efficient to do this. And by the way, that would be O of 1, wouldn't it, to do that part of it? But then once this 8 is up here, let me clean that up a little bit. Once this 8 is here, or we'll say it's here, the 70 is already gone. Now, the 8 has to swap with the max child, which is this one, isn't it? So the swap function's called, first that figures out which one is the max child, this one. So there's a swap. So the 8 is here, and the 60 is here. And this is 8. And then the 8, they find that the max child is found, and then a swap again. So 40 goes here, and 8 goes here. So it's reheaping down, isn't it? Finding its spot. So the same thing goes here. The 70 is removed. So the last one is put there, and then it reheaps down. It compares this one, and this one's the max child, so it swaps the two. And 60 goes here, and 8 goes here. And then it compares with its left and right children again to find the max child, which would be, well, what would it be? It'd be this one here. That's the left child. Or excuse me, let's see, how do we do this here? No, it'd be these two, wouldn't it? It'd be the 40 and the 30, although the 40 was swapped. Anyway, you get the idea. It's just going to reheap down going like this, just as it reheaps down going like this. Okay. So the principles of the heap reheaping up and down, likewise, when we insert here, that'd be the next available. Then we would insert here, then here, then here, then here, like that. And so when we'll just take it back to this point right here. To insert right here, that would be inserting right here, wouldn't it? So let's say we want to insert a 50. That'd be putting a 50 right there. Okay, so the shape is fine, but the order is not, because the parent has to be greater than both children. So it's not greater than 50, so there's a swap. 50 goes here, 12 goes here. So there's a swap with the 50 and the 12. 50 goes here, 12 goes here. Okay. And then it's back to its it maintains its order and shape properties, okay? So that's it. The point is the code uses an array, but the array uses the principles of a binary tree, a heap. It's pretty ingenious. I mean, in the sense that that the simple formulas of like root times 2 plus 1 and root times 2 plus 2, just to see the children, and then to compare the left child and the right child to find the max child. And that can all be done in here, or it can be done in here. So the same thing. And again, the whole idea of a priority queue is to create a queue that behaves like a queue, except that it's not first in, first out. Instead, it's really highest priority is first out. I'll just say highest priority is first out. Won't put that into an acronym. So, and of course, there's a need for that. We want to have a queue sometimes that doesn't always just output or dequeue the first one that went into it. Instead, we want to be able to dequeue the one that's most important and needs to be dequeued first, rather than just the first one that was inqueued. And that's kind of the essence of a priority queue. All right, so here is a heap, and or I guess you could say a priority queue, just implemented as a binary tree. And here's a priority queue. So, and remember that 2 times root plus 1 and root times 2 plus 2. So 0 times 2 plus 1. So same thing goes here. 0 times 2 plus 1, that's the left child. 0 times 2 plus, that's the right child. Okay, well, where I was going with this right now, so all I've done here is I've just put them into the array as they are right here. So the next one to be inqueued would actually be this level is full. So it would be right here. That'd be the next one to go in. So let's say, here it is, inqueue an 87. So it would go right here, which would be right here. Okay. So inqueuing, the actual process of inqueuing, well, or at least this part, would be O of 1, wouldn't it? It's easy just to put something at the end of the array. It wouldn't matter if there were 15 items in the array or if there were a million items. It's just O of 1 to put it at the end of the array. So that part is easy. But then it has to reheap up, right? It's heading up now. It's heading up. It's going to swap with its parent if it's greater than its parent, and it is. So it swaps. And so now the 87 is here, and the 20 is here. And then it compares to its parent, and it's greater, so it swaps again. It compares, oops, I goofed there. We'll say this is 82. Swaps with its parents again. Oh, no, it wouldn't. If this is 82 and this is 80, it's done. So that's as far as it goes up. It would just move up, bubble up, or reheap up to some given point. I don't know what that is. That's a 3, isn't it? So it would make it all the way to here. We're pretending like this is 82. So anyway, it reheaps up and stops right here because 80 is less than 82. Okay. So the process of heading up then is O of log n. Okay, oops, I guess I shouldn't have put the parentheses around that too. We'll do it like that. So O of 1 plus O of log n, O of 1 plus O of log n is O of log n. So the process of NQing overall is O of log n. Oops. Okay? And likewise to DQ, we pop this off. So that process of DQing, and of course the process, remember we take the last one and we move it up to here. So that process of removing that one and moving that up is O of 1. It doesn't matter if you have 15 items or 15 million items, removing that and moving that up are always constant time. So it's O of 1. But after this 87 is put up here, then it's reheaped down. Down. So now it's going to start heading back down. And it's going to do that by comparing, this one was 82 and this is 90. So, and what did we do? We moved in 80, we're DQing. We took that one off. So this one, I don't know, I guess this one went up, didn't it? It moved up somewhere. So it's this one right here. That's if this doesn't exist. There we go. So if that's where we are at this point, then this would be, in this level here, this is the rightmost one. So if this 100 is removed, then this one here, that's a 42, we'll say, it's moved up to here. That's O of 1. Removal and move, O of 1. Doesn't matter if this tree's got a million items. But now it's got to head back down by reheap down. And so it's going to swap, the 42 swaps with the 90, not the 82. It's going to swap with the max child. So now 90 is here, 42 is here, and then now it's going to swap with this. This is the max child, not the 50, the 60 is. So 60 is here. I already forgot what this was, 42, okay. And now, is it greater than both children? Yes, it is. So it stops right there. So this process of reheaping down is O of log n. So O of 1 to assign and remove and assign, and then O of log n. Add them together, it's O of log n. So NQ and DQ are O of log n because of the reheap up and the reheap down. All right, so here's a little extra credit assignment. We'll make it worth 1 point extra credit just for breathing and doing it. In that order, I guess. So just write the big O notation for NQ, DQ, swap, make empty, and then the destructor in the priority queue class. And just write these 5 things on a piece of paper or type it out, whatever, on Microsoft Word, and just email them to me, email, not Canvas, and we'll make it due the same day as the homework. I don't have that right in front of me, so whenever the homework is due, the extra credit, if you want to do it, has to be turned in by that day or sooner. And we'll call that a wrap. This will be the end of, it'll be the only video we'll do for lecture 9. It's not a real big lecture. The idea is just for you to understand what a priority queue is, and to a lesser extent what a heap is, or how they work together and so forth. And that's it.